Okay, yeah, perfect. Yeah. So thanks everyone. Like thanks for joining. And today we have Hassan here. So Hassan is working with Dan Brown. He's towards the completion of his PhD thesis, and he has this beautiful work on quantum error correction, which is actually very pedagogically written also. And we thought, like why not have Hassan here, present this work. Yeah, so Hassan, the stage is yours. Yeah.
Thank you. I'll start by sharing my screen. Can everyone see it fine? Yep. So first of all, thanks Kishore and Andrew for inviting me and giving me the opportunity to tell you about our work. This was the culmination of 1 year worth of effort. And today I'll be telling you about fault-tolerant logical Clifford gates from code automorphisms. And this work was a collaborative project between myself, Sergios Koutsimpas, and Mark Webster, who are postdocs in my group, and Abhishek, who is a postdoc in another group at UCL, and of course my professor, Professor Dan Brown. So I'll just jump straight into the motivation of our project. If you've been following the literature around QEC, you might have realized that companies are now experimenting with quantum memories. They are taking their physical qubits and they're taking a quantum stabilizer code and encoding information redundantly. And then they're using these stabilizer codes to extend the qubit lifetimes. But now, while these experiments have been remarkable, in particular, the Google experiment has shown an exponential suppression in errors as you scale up your code distance, the next open question is, how do we do logic in an error-corrected framework? And to that end, one needs to do operations on the logical information. You would like to process your encoded logical qubits without disturbing the fragile quantum information. And a substantial part of those operations will be Clifford operations, which you know is generated by the single qubit phase gate S, the Hadamard, and the 2-qubit CZ. These will be essential for universal quantum computing. And in our work, we were interested in the question of finding low overhead, short depth circuits that implement a logical Clifford gate. And I would like to emphasize that it is easy to find an implementation of a desired Clifford. You could just unencode from your code space, apply some gate, and then re-encode. But you would never want to do that in practice because that has high depth circuits and does not preserve distance. And I will not be talking a lot about what the stabilizer theory is, but since the title includes the words Clifford logical, maybe I thought I have a slide on what a Clifford logical operator is. First of all, what is a Clifford gate? So a Clifford gate is an operation that maps a Pauli to a Pauli. And then a logical Clifford operator will be a map that maps the stabilizer generators to independent products of stabilizer generators. In other words, it preserves the stabilizer group. This is a condition that needs to be satisfied by any circuit that corresponds to a logical operator. But in addition to this, a Clifford logical operator will act on the logical polys of your code, and it will map the logical poly generators to products of other logical polys. But this product will also include some products of stabilizer generators, and there will be some possible phases of I. And the map from these logical polys to some other logical polys can be described by a Clifford operator acting on your k logical qubits. So we wish to find these circuits exactly that map our original logical polys to some other logical polys. So directly, I would like to just tell you what our main results were in this investigation. So what we find is a set of algorithms that enumerate fault-tolerant Clifford logical operators using code and matrix automorphisms. I will give a definition and a distinction between these two types of automorphisms. And our methods do not require any qubit overhead. So this needs to be, for example, contrasted with more general techniques such as lattice surgery that rely on some auxiliary qubits and state preparation and measurement. And with that, you can do any sort of logic, not just Clifford. You can also do non-Clifford. And our approach is completely complementary to that. There will be a subclass of Clifford circuits that you can do with low overhead using automorphism gates, and then the rest you can do with lattice surgery uh, for low overhead computing overall. And our circuits are fault tolerant. They are equivalent to swap plus single qubit Clifford circuits. I will have a slide on this later and discuss their fault tolerance again. And I would like to also mention that our work relates to some papers that have already appeared in literature, and one that was actually published in 1997 called the GF4 paper by Calderbrand et al. So in our work, we formalize and extend some of the methods introduced in this paper. What they do is they present QEC codes as some codes over GF4, and then they have a paragraph where they say automorphisms of this code correspond to Clifford operators, and they have a binary representation that they use to understand these automorphisms, but they don't discuss it in depth, and in particular, they don't talk about the necessary Pauli corrections, which I will talk about. So, and furthermore, our work relates to fault-tolerant gates, fault transversal gates that have appeared in literature, particularly in reference 2 and 3 here. And our work generalizes these fault transversal gates from CSS codes to all stabilizer codes, including non-CSS codes. And we don't have to also just rely on Hadamard circuits. We can describe any single qubit Clifford fault transversal circuit using our techniques. And then I have a point here that also says that we can find circuits with 2 qubit Cliffords. We have a method of representing 2 qubit gates, such as a C0 and a CZ, as automorphisms as well. So we have a systematic way of finding some short depth circuits as well with 2 qubit gates. And I would also like to highlight our open source Python package, which you can download via pip or GitHub to play around with these things yourself. Oops. Okay, so here's our algorithm outline. The only input that's needed for our software will be the check matrix of a stabilizer code. And then we have a number of binary Pauli representations that we use. The user can choose which one they want to use in order to capture which Clifford subgroup they want to check for a particular code. And once you have that binary Pauli representation, it defines a classical binary linear code. And then you wish to compute automorphisms of that. And you can use either code automorphisms and matrix automorphisms. So in the original manuscript on arXiv, and I think still the current version on arXiv, only mentions code automorphisms. It will be hopefully updated soon, or in the published version of our paper, which relied on the proprietary licensed computer algebra software program called Magma. So it has what we saw was that it has at least the fastest way of computing code automorphism. So we were using it heavily for our work. But now we provide an alternative via matrix automorphisms that has an open source Python package. So you don't have to rely on Magma if you want to run through the whole algorithm now. And once we have a set of automorphisms for our classical binary linear codes, we understand those automorphism group generators as some valid physical circuits.
So Hasan, like, in this auto QEC, like in your package, it's like so now you have already incorporated a matrix automorphism in the updated version. I mean, like, it's not in the R5, but in auto QEC it's there.
Yeah, thanks for pointing that out. Yes, we have not put it in the manuscript, but it is online already, so people can already start using it.
Okay. Now, because like, I mean, we use this in our multivariate bicycle paper to find, like, but then we had to rely on magma, and for that we had some difficulty. Like
Right.
yeah, but yeah, I think
Okay.
it's good, like yeah. Okay.
Yeah, that's great then. Uh, and so once we have this set of automorphisms, we understand them as some physical circuits, and then we have a number of steps where we map from these permutations onto a symplectic matrix, and then that symplectic matrix is the circuit. We find the Pauli correction that is essential to preserve the stabilizer group, and then we have a circuit acting on the n qubits of the stabilizer code. And the next step is to understand its action on the k logical qubits, which is step 6, and write that down as a circuit as well. So the output is two circuits, actually, one acting on the n qubits. Oh, sorry, I think there's a fire alarm, but it's not in my build. Oh,
Oh.
I'm really sorry about this.
I mean, we
Hopefully
don't hear it,
it's
but
a
I think you need to, like, do you need to leave the building? We don't want you to be
yeah.
get sacrificed because of fire or something.
Okay, I think it was a drill. It was a drill. It just stopped.
Ah, okay, 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 okay.
Sorry about this. Yeah, I think my headphones might have cut it out for you
No, no,
guys,
no.
but it was
The
quite loud.
SCFSP quantum error correction seminars don't take responsibility. Okay.
Yeah.
Okay. So
Yeah.
basically, like, if you understand Hassan, like so like, let's say you start with this binary poly representation. So at that part, like, it's totally classical stuff, and you are basically finding this matrix automorphisms, which is all possible automorphism, which is a very large set. It will be like, there will be many objects there, right? But then you are saying you are only interested in which, like, allow for some nice fault tolerant characteristic, like something which swap plus valid Clifford gate or something, and then
Yeah.
you come back to again the quantum world via converting it to symplectic matrix and poly correction, whatever, and logical
Yes.
action.
Yeah. It will become more evident in my next slides.
Okay, 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 okay.
How automorphisms map onto these valid Clifford circuits, but most of them already correspond to valid fault-tolerant Clifford
I
circuits
see.
that are of
I
this
see.
form.
I see. I see.
Because of the way we represent the code, we kind of enforce it to have those kind of automorphisms. Yeah, maybe when I come to the slide, if it's not clear again, yeah, we can circle back to it.
Okay. Yeah.
But before moving on any further, let me show you the three types of circuits that our software can find. The first one is the gold standard transversal gates, which are which are directly fault tolerant because they act on single qubits, so they don't propagate errors to multiple physical qubits. And then the second class is the most interesting class to have come out of our work, I think, because here, by also adding swap gates into your physical gates instruction, you get increased logical computational capabilities, and you can argue that if the qubit permutations are facilitated by no direct interaction between these two qubits, if you have like optical tweezers and if you're just moving qubits around, then these circuits are also fault tolerant. And even for superconducting circuits, you can design fault tolerant swap gadgets by swapping via ancillas and then resetting. So I think it's a very interesting class of circuits. And then the final one is general Clifford gates. So as I said, we can also describe C0 gates as automorphisms. And these will be fault tolerant under certain conditions. For example, if the C0s are between two blocks of codes, then they are transversal. So the error correcting code can handle errors in that case. But I will not focus very much on these type of circuits in my talk today. Okay, onto our two types of automorphisms. The first one is code automorphisms. These are permutations that correspond to some swap transversal Clifford circuits that preserve the whole stabilizer group. So it is the all possible set of swap transversal Clifford circuits that a code supports. And this can be slow. Computing this can be slow, and it relies on magma. However, the alternative is matrix automorphisms, which help you identify a subgroup of the code automorphisms by just looking at permutations that preserve the stabilizer generators rather than the whole group. So it maps a set of stabilizer generators among themselves. The benefit is that this is very, very fast. So you can study very, very large stabilizer codes now and try to look for fault-tolerant circuits. And the other advantage is that it's open source. And what we have seen is that sometimes this subgroup that you identify matches the code automorphism group. In particular, for bivariate bicycle codes, we get the same automorphism group order using either technique. So we don't have to use magma at all while studying bivariate bicycle codes. And before moving any further, I wanted to have a little animation of the simplest automorphism gate that I could think of. And for that, I took the simplest error correcting code I could think of, which is the 422 code. As you know, it has wait for stabilizers acting on all 4 qubits, XXX and ZZZZ. And then it has the logical operators at the left, bottom left. And you can represent these pictorially on the right. So for example, you have the X1 logical shown as a line in red, and then the Z1 logical is a vertical line that overlaps with it on 1 qubit. So they anti-commute as expected. And then you have the second logical at the bottom. And when you look at the stabilizers, you see that any swap, any permutation of these 4 qubits would preserve these stabilizers. So let's, for example, swap 1 and 2. And while that has trivial action on the stabilizer group, as you can see, it has moved our logicals. So for example, it left X1 and Z2 invariant, but it moved Z1 to a product of Z1 and Z2, and then X2 to a product of X1 and X2, which is precisely the action of a logical CNOT gate. So this is the intuition of simple automorphism gates. Now let's formalize this more and do it in an algorithmic way. So in our algorithm, we start with the standard symplectic matrix representation. We write the stabilizers as some binary matrix with their X and Z supports, which for a CSS code admits this block diagonal form. And now we will consider automorphisms defined by this binary linear code. So we will look for column permutations that preserve the span of the rows. So if we take, for example, one of the qubits with its corresponding X and Z support, identified by column I and column n plus I, if you were to swap these two columns, you see that since you're swapping the X and Z support, it corresponds to a Hadamard gate. And then if you take a pair of qubits with their corresponding columns, and if you swap the columns within the blocks, that corresponds to a swap gate. So when you find the automorphism group of this binary linear code, the generators will tell you all possible Hadamard plus swap circuits. And a key identification of our work was that we're not restricted only by this particular 2-block representation. Why not take any arbitrary 2-block representation and look for the other symmetries? So you can also define this third block, which is the first and second block added up, mod 2. And then if you, for example, swap the GZ block and the XZ block, you get S swap circuits. And then if you swap the red and the blue, you get square root of X gates, which is Hadamard S Hadamard. And then the next question is, well, is a 2-block representation enough to recover all symmetries? And the short answer is no. Sometimes you need this whole 3-block representation because there are some gates known by various names in literature, actually. They're called gamma gates, facet gates, but they are a product of SNH gates. So for example, the SH gate has an order 3 symmetry if we ignore the phases, which we are now because we're not dealing with polys yet. But so an SH gate would permute the whole poly bases together. So it would map X to Z, Z to Y, and Y to X. So sometimes we need the whole 3-block representation to recover all symmetries. And here I wanted to give you another simple example. I wanted to show you the binary representation of the 513 code. So at the top, you can see its stabilizer generators, and the table shows you the stabilizer generators written in binary form. So if you just close the blue block and look at the red and green, that is the standard parity check matrix of the 513 code. And then you define the third block. And now you can find the automorphisms of this binary linear code. And then the next additional step, which was what your question was about, was making sure that all the automorphisms you get are valid swap transversal circuits. And to do this, we use a general classical binary linear code, which has 3 blocks of identities. So it's an n by 3n matrix. And the automorphisms of this code correspond to all possible swap transversal circuits. So taking an intersection of the automorphism group for the stabilizer code with the automorphism group of this classical code restricts you within the space of valid swap transversal circuits. And then code embedding. So we can only describe H, S, and swap gates by automorphisms. So we need something additional if we wish to also describe 2-qubit gates. And what we use is something known as code embedding. And essentially what this corresponds to is adding extra columns to the 3-block representation that I have just shown. And these extra columns will correspond to pairs of qubits. So it will be, for example, the column, the first column of qubit 1, and then the first column of qubit 2 added together. And then swaps within this larger code will correspond to CNOT gates. If you swap this extra column with, for example, the original column of the qubit, that looks like a CNOT gate. And you can choose what CNOTs you allow. So you can tailor this to the connectivity of a device, for example, by appending only certain columns that correspond to pairs of qubits. So that is one way of restricting the depth of your circuits. However, as I said, sometimes this method might lead to high depth circuits, and we wish to avoid that. You don't want to find a circuit that actually unencodes your stabilizer code, but still it might have some use case. And then in this slide, I summarize our automorphism algorithm family. So the different binary representations that one might use to recover different types of logical Clifford circuits. I have shown you what the Hadamard plus swap would look like. It actually has the standard parity check matrix as the binary representation. So no further steps needed. And the Clifford gate restriction would be an n by 2n classical binary linear code. And then you can take this original by a symplectic representation and then transform it with the corresponding matrices in the transformation matrix column to get the correct binary representation for the other symmetries. And the most general one is the fourth one that can recover all swap transversal Clifford gates. Now I'm circling back to the algorithm outline and telling you that we have so far covered up to point 3. We have talked about the poly representation. We have talked about the different types of automorphisms and the Clifford restriction that we enforce. Now I will tell you about steps 4, 5, 6, and 7. So converting permutations to a symplectic matrix. Right now we have a set of permutations that generate the automorphism group of the binary linear code. And from these are given in cyclic notation. We can convert these into a matrix representation. And then if we conjugate each generator P by this transformation matrix that I had just shown in the previous slide, we will recover the symplectic matrix representation. So for the 2-block representation, this will directly be what we are looking for. US will be interpreted as a Clifford circuit. And then for the 3-block representation, we get this block diagonal form where we only care about the first block because that corresponds to the X and the Z part. And the third block is just the XZ block. So we don't care about the action in that sector. And the symplectic matrix can be written down as a Clifford circuit. And as I said many times now, it corresponds to this swap transversal circuit with Hadamard and S gates. So this is the physical circuit still acting on the n qubits. Yep. And then Pauli corrections. So firstly, why might one need Pauli corrections? It is because conjugation by Cliffords can cause a sign change to stabilizers. For example, if you have a non-CSS code, you might have some Y Pauli operators, and under the action of Hadamard, Y would get mapped to -Y. But even for CSS codes, if you are dealing with S gates, for example, an S gate would map X to Y, and then there's a hidden phase of I in there, which might lead to some issues. So you have to make sure you do the right Pauli corrections. And to calculate the Pauli correction, we start with no correction, and then we refer to the destabilizers of the stabilizer code. A quick definition for these. So these are a set of operators that anti-commute with one and only one stabilizer, and they commute with the logicals of the code. So we conjugate each stabilizer by the symplectic matrix we found, which will yield a product of stabilizers up to a sign. And we compare that sign with what is expected. And if the sign is -1, we can fix it by just multiplying UP with the corresponding destabilizer. So that will give us a set of Pauli corrections that we can then prepend to our circuit. So at the end, we now have our n-qubit circuit that preserves the stabilizer group, including the signs. So the next step is, what is the action on the k logical qubits? For this step, you need a symplectic logical basis. And as in simpler terms, you need pairs of anti-commuting logicals. And then you need to find the action of this of the physical circuit on the logicals. And you can do this by right multiplication on the logical Paulis. And then we will identify where these logical Paulis get mapped to. And we can do this by this equation at the bottom. I can break it down. So here we have a symplectic product between the original anti-commutators. So if you look at the right side, LX and LZ have been switched because we wish to check the anti-commutation. And then on the left side from the omega, the symplectic norm, you have the new Paulis. So essentially what we are doing is we are checking the anti-commutation of the new logical Paulis with the original logical Paulis to understand where the original Paulis got mapped to. And this gives another symplectic matrix called UACT, which we call UACT. And UACT, we now need to write it down as a circuit so that we understand what it is. And now it can be a general Clifford, which is an important point. It is no longer restricted to just swap transversal circuits. So swap transversal circuits have a more complicated logical action than they do on the physical qubits, which is nice because you can get C0 gates by just, for example, swap gates, as I had shown you for the 422 code example. And we have introduced this particular tableau decomposition, which consists of an overcomplete set of gates, but it had been very useful in breaking down the symplectic matrix into a circuit form. This particular representation is very natural for symplectic matrices. So we write our circuits down with these gates, And then we also need a polycorrection at the logical level, but I don't have to go into depth into this because it's very similar to the polycorrection for the physical circuit. And it is in fact incorporated into that method. And then finally, our final logical action is you act. So now we have our n-qubit logical Clifford circuit correspond to some k logical qubit Clifford circuit on the logical qubits. Okay. Now I'll move on to results. We started with the library of best known distance codes. This is available on codetables.de. And we have studied codes for up to n equals 30, and we have seen some interesting results for the one logical qubit codes. And what we have observed is that actually most of them have the full single qubit Clifford group by swap transversal gates. And we compared this with their set of transversal gates. So if you look at the second column, you see that only one code has both S and H, and most of them have only trivial transversal gates. And the code that has SNH, by the way, is the Sting code, the 713 code. And then a couple have either just S gates or SH gates. And the picture changes completely when you consider swap transversal gates. And in the end, you see that most of these best known distance codes, most of which are non-CSS, now have addressable swap transversal logical SNH gates. So they could form interesting code families for experiments, for example, because they're quite high distance. They're the codes with the best known distance. So they form an interesting case study. And onto our other results bivariate bicycle codes. As you might know, BB codes are a very promising family of practical quantum LDPC codes. They have a much higher encoding rate than the surface code, and their connectivity is not too much more complex than the surface code. So we wanted to study their logical Clifford circuits. And in fact, in the original Nature paper, the authors have already looked at two types of logical Clifford circuits. And these are automorphisms that move qubits either horizontally or vertically. So these are the cyclic shift automorphisms. And then they also identify one type of ZX duality that maps X and Z stabilizers onto one another. So in our work, we find the whole code automorphism group for the BB codes, and we identify additional swap transversal logical Clifford circuits not classified by these two categories above. And then we also find the logical actions of all these circuits and append them with polycorrections if necessary. And I have a table here summarizing our results. So we were able to find code automorphisms up to the n equals 360 code, and column 2 illustrates the order of the code automorphism group. And then the third column is the automorphism group order reported by IBM. As you can see, the order of the full code automorphism group is at least 2 times that identified by IBM. And in particular, for some codes, it is much larger. For example, for the 72 qubit code, it's as large as 12 times more. So it's interesting what these additional circuits might be helpful for. And I also wanted to show you pictorially an example of the logical action of these various automorphism gates. So in IBM's work, I have here included a circuit that corresponds to some horizontal shift on the grid. So if you shift all the qubits with respect to the stabilizers, you get some sort of logical action that is symmetric onto the two classes of logical qubits that they have. If you're familiar with the paper, they partition their logical qubits into two blocks called the unprimed and the primed block. And in our work, the additional generators we find turn out to have some 2-qubit gates that go across these primed and unprimed blocks. And a natural question we get is, how hard is it to compute automorphism groups? And to give you an idea, I report on some results for the BB codes. Let's first talk about the 3-block representation, which is able to recover all subtransversal circuits of stabilizer codes. It relies on magma because it computes code automorphisms, and it corresponds to this blue line on the top. As you can see, it has a sort of still reasonable time for even the 144 code. It took about 2 hours and 10 minutes to compute the automorphisms of that code. But you can see that it has an exponential scaling. And in fact, we couldn't study larger BB codes using this representation. But just algebraically, we know what kind of symmetries BB codes can support. It is just ZX dualities. So we can restrict our binary representation to the correct 2-block representation and compute code automorphisms of that. And as you can see, the 2-block representation is exponentially faster than the 3-block representation. But again, it has an exponential scaling, so it only allowed us to study the 2 more larger codes, the 288 and 360 code. And again, this uses code automorphisms, which relies on magma. And then finally,
But
the
why do you
result.
have this number dropping? Like, I mean, so like the orange
Yes,
line.
yeah, I think if I go back a few slides, I think it's because the 288 code has a large code automorphism group compared to the
Uh,
361. So it took more time to enumerate all of those. That's our that's our conjecture. But
I see.
yeah, it's interesting. It's the automorphism group scaling is not, the time taken is not, yeah,
Maybe let's say, like, I mean, once you have calculated the size of the automorphism group, and then you plot it against, instead of a code block length, the automorphism group size, then will you get a, like a consistent picture? I don't know. Like, do you
as
expect to
in,
get? So basically, I'm saying that, like, I mean, in your x-axis, just put, like automorphism group size.
okay.
Yeah,
Uh,
and then maybe you don't have, like this suddenly, like, I mean, so like I mean, then
right.
as you increase the size, then the time taken will be large, maybe. I mean,
Yeah.
I mean,
Yeah, it's,
just to test your conjecture, like, yeah, yeah.
yeah. Sure, yes. And the time it takes depends on something called the hull of the binary linear code. So which corresponds to its intersection with its dual. So it might relate to that for this code. Um, for that, I will have to refer you to the Leon's algorithm, which is the algorithm used to compute these things.
I
Um,
see.
yeah. And the most exciting line on this graph, as you might agree, is the green line, because it seems to have this quasi, like, almost linear or like polynomial scaling. And um, we used an open source package to find these matrix automorphisms, and we were able to find even the automorphisms of the largest BB code in the original paper, which is the 756
So,
56
so
code.
can you remind, like, Hassan, like, what was the difference between the matrix automorphism and code automorphism? Like, is it that in matrix automorphism you are looking only a subset of code automorphisms?
Um, Yes, so the code automorphisms correspond to the permutations so in terms of the matrix representation, it will be column permutations that preserve the span of the rows. So, but the matrix automorphism will just be a permutation of the rows, and it won't be the whole span. So it typically corresponds to a subgroup, but in the case of BB codes, it recovers the whole code automorphism group. The
Yeah,
reason for that being, yeah,
No, no, please continue. Huh?
The reason for this is the BB codes are already represented in a very nice basis that is overcomplete. So you have, it's not a full rank matrix. It has some extra rows, and the weight of these rows are the same. And automorphisms are weight preserving permutations.
I
So
see.
we think, we haven't formally proven, but we conjecture that matrix automorphisms are sufficient to recover the whole code automorphism group. It all depends on,
In BB code, I see.
yeah, which representation you take for
Okay,
the
I
stabilizer
see. Because,
generators.
like, I mean, another thing is that, like the circuits that you got, let's say for a particular logical Clifford, I mean, is that optimal if you are looking at, like only a subset, like, optimal in the sense of, like depth, like there can be many different representations possible, right?
Right. For the physical circuits,
Yeah,
you mean?
the physical circuit for the logical gate.
Yep. Yeah. I think they're mostly. Oh, actually, I'm not sure. So they have one layer of single qubit Cliffords and then some permutations, but those permutations might be order 2 or more. So not sure, but for sure, like if you're once you start thinking about a geometry, I think it's important to optimize these permutations such that most of them are done in parallel. Yeah. Okay, and actually that concludes the first part of my talk, but I wanted to take this opportunity to tell you very briefly about our follow-up work, which was a direct extension to this previous paper, where we moved on from logical gates and started thinking about decoding, because now we have a very efficient way of identifying symmetries for stabilizer codes. And the natural question was, oh, can these symmetries help with decoding problems? And it turns out that they do. So we introduced a novel decoder, which we call an automorphism ensemble decoder. I will explain it very briefly, but first let me say that automorphism ensemble decoders already exist, but in the classical coding theory. So they do use these particularly for LDPC codes or Reed-Muller codes. So we wanted to map this onto the quantum case and study quantum LDPC codes. And in particular, since we were looking at bivariate bicycle codes, we focused on that. So the automorphism ensemble decoder is essentially a set of BP decoders, one of which is your original belief propagation decoder. You normally pass a syndrome to BP, get an output, and sometimes that output is not good. In most cases, it's not good for the quantum codes. And therefore, you do some extra classical post-processing, such as ordered statistics decoding. So you have this whole BP plus OSD decoder to find the right corrections. But instead, we thought about having an ensemble of just BP decoders, so multiple BP decoders, and with each one receiving a transformed syndrome. And the way we transform the syndrome that we send to these constituent BP decoders is via code automorphisms. So we find the linear map that changes this syndrome according to some automorphism and pass these permuted syndromes to each BP decoder. And in this plot, I show you some results for circuit level noise. This is for the 7212.6 BB code. The orange line is BP, and the blue line is BP plus OSD0. And then you see 3 ensemble decoders. And as you see, as we systematically increase the number of constituent BP decoders in the ensemble, we approach and outperform OSD performance. So the key takeaway is that we have, if parallelized, we have BP speed with OSD accuracy for circuit level noise. And you can read our paper. I have included the QR code and the relevant archive number. And then, of course, we also tried this for the larger BP codes. Here I contrast BP plus OSD, and alt BP in the middle. As you can see, as the code size increases, BP starts not performing so well. And you can improve upon this by just parallel BP decoders, each receiving a transformed syndrome, and you approach or sometimes match OSD 0 level accuracy. So, yep. And we are doing circuit level noise simulations. So here, the automorphisms that I'm talking about are actually not the automorphisms of the BB codes, but rather the automorphisms of their detector error models, which are huge matrices tracking all error mechanisms. And it's impressive, I think, that the open source package that we use, which is called PyBliss, can find the automorphism group orders for these very large binary matrices in such little time. As you can see, even for the 756 code, it took like 1/10 of a second. So it's very promising to study, for studying larger and larger codes. Okay, so I want to move on to conclusions. What we do is we introduce a systematic way of finding logical gates through automorphisms. And in doing so, we also find many new fault-tolerant logical Clifford gates. And we have also introduced an automorphism ensemble decoder for bivariate bicycle codes. So the big key takeaway should be that large code automorphism groups are desirable for logical gates and also for efficient and accurate decoding. Hence, we think they are very important for QEC design, especially when used in a complementary way to other techniques. So with that, I want to finish off with my final slides and provide links to our papers and the GitHub packages. And thank you.
Yeah, very nice. Thanks, Hassan. This was very nicely presented seminar, and this
Thank you.
odd QC and odd DEC, I think they will be very useful for the community. So if
Oh,
people
thank
have
you.
any
Yeah.
question, please just unmute yourself and ask. You know, like-
Yeah, thank you very much for the talk. That's extremely nice.
Thank you.
So I was wondering, maybe you comment on this, but maybe I didn't understand fully. So using this code algorithms, can you find all possible swap transversal gates, or you only find a subset?
So we can find all possible swap-transversal circuits that the code supports. Yes. Like if the stabilizer code supports a particular swap-transversal gate, it will be identified.
Right,
If
so
you can
find all
find
of
the
them that
full
exist.
yes, all of them that exist, yes.
And distinguish, so in your code, right, you have like these different way of generating code out of this, right? There's a direct way, and there's one by a duality, the XY or ZX or ZY dualities, right?
Yes.
I don't understand what's the difference of them, or what's the, because they seem to give different
Yeah.
automorphism groups, if I understand correctly.
Yeah. So those correspond to maybe I should have. Okay. Those different things correspond to the different rows in this table, the different binary representations. So for example, row 1 would be ZX duality, and row 2 is, I think, ZY. I might be wrong. And then the last one is XY duality. Or the opposite, sorry. Yeah. So but essentially, yes, the Python scripts with the names ZX and ZY essentially correspond to these kind of representations.
But if you combine all groups, you would basically get all the possible swap transversal gates.
Yeah, so
they give different results,
what
right?
I was
for different rows.
Yeah, you get different results. I think the best approach is probably taking any two block representation, maybe the ZX duality and one more, and that should give you almost all probably like symmetries, but there are some peculiar codes with order 3 symmetries for which you really need the full code automorphism group. So for that, you would need row 4 here, where you have 3 blocks in your representation, and then that recovers also these order 3 symmetries. But if you only have like these order 2 symmetries, the best approach is to use, as I said, just two pairs of 2 blocks, kind of. Yeah. Sorry, 1 pair of 2 blocks. Yeah.
Right. And basically you have these 4 different ZX, XY, and sorry, ZX, ZY, and XZ or something. I forgot. And also the standard one. But I noticed the standard one runs way slower, like in Magma. Is there a reason for that?
Yeah. I guess it relates to this. Yeah, the 3 block representation is quite slower than the 2 block representation, because the search space is larger.
Right. So 3 will correspond to the non-duality one, right? In your
Yes,
code,
the
right?
3 block. Yeah, that's just the full code automorphism group. That will correspond to all possible swap transversal gates, and not just ZX duality or some other kind of duality.
Okay, that's why it's slow. Okay, cool. Thanks.
But I mean, with matrix automorphisms, you can maybe find some sort of subgroup, and yeah. And as I said, for example, for BB codes, you actually never need the 3 block representation, because you know a priori that they only have ZX dualities. So yeah. And by the way, I think forgot to mention, but the link here is the like would refer you to the subdirectory where we do these matrix automorphisms, in case someone wants to try them out. So as I said, it's not on the paper. It will be on the paper as well very soon, but it's already on GitHub at this link.
So just one quick question. So from this automorphism, is there a way that I guess like you could think of to get like a measurement sequence instead of like gates? So I'm thinking like from the perspective of kind of like this Floquet codes, because like you could have like this sequence of measurement where after 3 rounds of measurements, like you kind of like perform like effectively a Hadamard gate. I don't know if that's like something that you could identify, like the measurement sequence, I mean, like from this code automorphisms.
Yeah. Yeah, that's a very interesting question, because Floquet codes are, as you said, are dynamically changing. So maybe the supported logicals change, and also just by doing the measurements, you implement some sort of gate. So short answer is I don't know. Maybe automorphisms can be useful in that sense as well. Maybe, as you said, to define the measurement schedule to kind of implement a specific logical Clifford gate. Yeah,
Yeah,
but
like
it's a
maybe one is
curious idea.
similar to like matrix or automorphism group, maybe dynamic automorphism group, like one needs to be defined, and then from there, so I think one needs to extend this to the dynamical case, like yeah, Andrew, you already know like what I'm saying, but yeah, I think one needs to maybe think of how to extend it for the like the dynamic case where the subspace is changing.
Yeah, because I think like it would be like a nice systematic way of identifying this sequence of measurements, like like this measurement schedule, where you could implement some logical operations effectively from that measurement schedule. Because people have just like come up with this, like just out of thin
That's
air.
very interesting.
Yeah. And yeah, like and basically, and there when you like fix number of cycles to be, let's say, 1, then maybe it will give you back like what Hasan has presented. Yeah,
exactly.
Right.
Yeah.
Yeah, it could be an interesting generalization to Floquet codes. Yeah.
Okay, interesting. Okay, so I think we will like, let me stop the recording now. We will stop here. Like, feel free to keep discussing. So I will just stop the recording.